Good evening, everyone. My name is Gursimran Singh. I am a PhD candidate at Rochester Institute of Technology, and today I'll be presenting our comprehensive survey on programmable data planes for network security. It is a joint work. It is a joint work with Dr. H.P. Acharya from Oklahoma State University and Dr. Minseok Kwon from Rochester Institute of Technology. Our research analyzes how the programmable switches and the P4 language are impacting the network security, uh, through customized line rate packet processing. So let me begin by addressing the fundamental challenge that today's network face from increasing number of threats. We are dealing with sophisticated cyber attacks that require not just detection, but rapid and adaptive responses. And although there are traditional equipment available, the problem with traditional networking equipment is first, it's built with closed design where the network operators can only use facilities that are hard coded by the manufacturers. Second, the traditional software based security solutions create significant bottlenecks and prevent line rate processing. Additionally, we are operating at a scale where we need terabyte level real-time threat detection. These limitations force us to choose between security and performance. However, a choice it is a choice that's becoming increasingly unsustainable as the sophistication of attacks grows. For instance, from Cloudflare's report from a few years ago, it showed that almost all large-scale layer 3 DDoS attacks still rely on IP spoofing attack, which is a relatively simple attack that should not that we should be able to defend against very effectively. Yet, the traditional solutions suffer from latency issues with response times ranging from 1 to over 100 milliseconds. At the same time, we need real-time threat detection at terabyte scale uh, to handle these kinds of situations. The figure on the right here shows a typical IP spoofing attack scenario. It's conceptually very simple, but defending against it at line rate while maintaining low latency has become challenging with traditional approaches. To get to a solution, understanding the evolution of network control is really important. We have moved through three major phases. First, the traditional networks that are closed, vendor-specific hardware. Next came the software-defined network with centralized control plane. And finally, moving to programmable data planes that enable customized packet processing directly in the switches. Programming protocol independent packet processors, or P4, has emerged as the most widely known and used language for programmable data planes. And this represents a fundamental shift from passive packet forwarding to an active, intelligent network processing. So a bit about P4 language. So P4 is domain-specific language that allows network administrators, not just the equipment manufacturers, they allow the administrators to define how packets are processed. For example, if a big vendor like Cisco that has manufactured switches and sells that to a corporation like on a large corporation like Google, and they want to use and customize those switches, and I'm assuming here they are traditional switches, they can't easily do that. For that, they might have to make their own switches or their own version of switches. However, for small businesses or small companies, it might be infeasible. In this case, programmable data plane and P4 plays a very important role and comes in very handy. Um, Second, it's protocol independent. That means that it can support any packet format and operates on match action paradigm that provides flexible packet processing pipelines. The key insight here is that P4 puts the power of packet processing and customization of packet processing directly in the hands of network operators, allowing them to respond to any new threats and requirements without waiting for vendor updates. The P4 architecture consists of three main programmable components. First, the programmable parser, which performs custom packet header extraction. Next is the match action pipeline that processes packets through multiple stages. And finally, the programmable deparser that reconstructs the packet for forwarding. As you can see in the pipeline diagram here, the packet flows through the parser, which extracts the packet headers into a series of match action units, each capable of examining the packet fields and executing actions based on the matches found. And finally, there is deparser that reassembles the packet before they exit the data plane. And this flexibility is what has allowed the security applications that we are going to discuss next to be able to be implemented in the data plane. The performance characteristic of these switches. So some of the performance characteristics is, first, these switches operate at multiple terabyte per second. For example, Tofino 1 chip based switches could be 3.2 to 6.4 Tbps, could get that much throughput. The pipeline architectures for these switches uses multiple stages, with each of them having access to SRAM, TCAM, which both of them are different kinds of memory, as well as ALU. However, in order to achieve this much speed, they have intentionally limited operations to simple types of operations like bit manipulation or basic arithmetic. These performance benefits comes with some important constraints. First, the parser can only handle fixed length fields from given offsets, making the complex protocols like HTTP with optional and variable header fields challenging to parse completely. Next, the instruction set has restrictions. It doesn't have any floating point operations. It doesn't have any division or any complex arithmetic operations. And it doesn't have any encryption primitives in any of the standard P4 architecture. Additionally, there is very limited on-chip memory. We are talking in terms of tens to hundreds of megabytes for some switches shared for all different functions. And this design guided by all these constraints is the crucial is crucial to understanding both the capabilities as well as limitations of P4-based programmable data plane and all these security solutions and innovation design techniques that are developed by the researchers. So our research systematically analyzes programmable data plane security across three major categories. First, in-network attack mitigation, where the switches act as smart switches. Second, the middle boxes in firewalls, providing security appliance functionality. And third, machine learning-based security for intelligent networks. We also highlight non-obvious design techniques that makes complex security functions feasible on programmable data plane despite hardware constraints, and identify challenges and future research directions. Let's begin with the first category. So using programmable switches as enhanced packet forwarding devices, even though this is a very basic role, these switches can provide traditional switch functionality with enhanced security capabilities, line rate threat detection and mitigation, superior performance compared to software-based solutions, and significantly lower cost than dedicated hardware. We are talking, if we are comparing one programmable data plane switch, which costs between $5,000 to $10,000 in comparison to millions of dollars for dedicated hardware. Some of the key applications for this category are anti-spoofing mechanisms and DDoS attack detection and mitigation, with different systems achieving sub-microsecond response times. Let me highlight three anti-spoofing systems that we discussed. First, the NetHCF. This paper maintains IP to hop count mapping in the form of tables to detect spoof traffic by comparing hop counts with the expected legitimate values. And it also uses a hybrid storage architecture where the controller stores the full table, and some of the most active IP entries are cached in the data plane using the registers. Next, the drop paper takes a different approach. It uses hash-based detection that calculates hash of source IP and MAC address, and it compares it against stored values in registers. And this system can identify and block spoof packets at line rate with real-time attack flagging. Then there is P4DAD, which focuses specifically on IPv6 security, storing IPv6 address to port bindings similar to a DHCP binding table, which has IP and MAC, and provides neighbor advertisement protection to prevent attackers from disrupting the IPv6 address configuration process. So all these capabilities, these were still available in earlier switches. However, programming data plane switches enhanced them by providing more efficient functionality and line rate throughput. For DDoS protection, we see both detection algorithms and complete systems. On the detection side, for heavy hitter flow detection, first we see HashPipe, which uses a pipeline of hash tables to identify K heaviest flows with high accuracy entirely in the data plane. The precision paper monitors a small fraction of packets for second pipeline traversal using probabilistic recirculation, optimizing between memory constraints and detection accuracy. For complete systems that do both detection and mitigation, Kwon implements switch native DDoS detection and mitigation, covering wide range of volumetric attacks designed specifically for ISP scale deployment. Finally, Poseidon provides an expressive policy language to specify DDoS attack mitigation strategies with functionality split between P4 switches and general purpose servers. And it's adaptive and it can generate new policies and reconfigure switch dynamically. All these systems also demonstrate response times in orders of magnitude faster than traditional solutions. Now moving to the second category, which is programmable, which is the middle box, programmable switches as middle boxes. Programmable switches have increasingly served as middle boxes and firewalls. Traditional firewalls functions adapted into programmable data plane include P4 guard, which provides policy language is match action table, which is translated by the controller and implements firewall rules based on IP, TCP, UDP, and ARP headers with statistical monitoring. Another example of this is CoFilter, which provides stateful filtering using 5-tuple hashing as flow IDs with a management server to update flow tables over time to avoid any hash collisions. In addition to that, some advanced capabilities deployed in programmable data plane that really set these systems apart is deep packet inspection using recirculate and truncate approach, and cryptographic primitives with lookup table implementation. So now we want to focus on one of the major breakthroughs in the field, enabling deep packet inspection in P4 despite P4 parsers limitations. The challenge is that P4 parsers are single pass with no support for loops, making complex payload parsing impossible through traditional means. And it was also stated in earlier P416 documentation that programmable data plane is not meant for DPI. However, a solution was discovered for it. The solution is the recirculate and truncate technique. The packets are recirculated through the switch pipeline multiple times with byte-by-byte processing on each pass. This combined with DFA, which is this combined with DFA implementation, which is deterministic finite automata, in match action pipeline within the match action tables to track state across multiple passes, enabling complex pattern matching in the line rate. To give you an example, so actually multiple examples. There are three systems here to demonstrate this capability. First was PPS, which was the first DFA-based implementation, mapping DFA transition to match action pipeline stages. In this process, the whole packet was consumed, and this supported thousands of keyword patterns at 10 plus Gbps speed, significantly outperforming CPU and FPGA-based implementations. Next, Deeper used cloned packet processing to overcome the packet consumption of the PPS, along with recirculate and truncate. It recirculated the cloned packet while keeping the original packet untouched. This handles thousands of patterns with URL backlist in real time and represents full next generation firewall implementation in P4. Next, in bold paper, which addressed the challenge of large rule sets that cause DFA state explosion. It used k-stride processing, which means processing multiple bytes per step or per pass to reduce pipeline depth, and it employed bit slicing for compact transition logic representation in the data plane. This diagram here shows how this system works for Deeper as an example. As you can see, the first packet arrives, then it's being cloned, and then both the packets are recirculated. Then the cloned packet is being analyzed and inspected to detect any malicious patterns, while the original packet keeps on recirculating until a decision is reached. This is a form of deep packet inspection done on programmable switches. For cryptographic functionality, Chen's paper on AES encryption, AES encryption implementation utilize scrambled lookup tables to implement different variants of AES and achieve 10 Gbps, 8 Gbps, and 7 Gbps throughput for AES 128, 192, and 256 respectively. In addition to that, there are some implementation of complete protocols in the programmable data plane, including P4 MaxSec, which is point-to-point LAN security with two-tier control architecture in which there is a local and central controller, along with P4 IPsec, which implements ESP protocol with AES CTR and null ciphers, relying on SDN controller for security association management. The key limitation with these systems that we have observed across all different implementation is the need for external dependencies for complex cryptographic operations, which can compromise the performance gains that we are seeking in the data plane. The Chen's AES implementation is shown here, an example. So first, this first image is basically an example of normal AES in which there are two steps like add round key, which is a XOR operation between round key and the data. And its result is then utilized for the sub-byte step, which applies S-box substitution lookup. And sub-bytes is dependent on the add round key. However, the scrambled lookup table technique is designed to reduce the number of sequential arithmetic operators required for AES. And by utilizing the table matching capability available on the programmable switches, this means that they pre-compute the lookup tables uh, before any of the actual computation. And we can complete both add round key and sub bytes in one lookup at the cost of storing additional lookup tables for each encryption round, as each byte is now different with different scrambled lookup tables. But this is an example how reducing the dependency and how they are able to fit the AES encryption in the data plane. Now moving to the third category, which represents the ML-based security in programmable data planes. We see successful applications across 4 key domains. For intrusion detection systems, we saw planter and sorter with nanosecond level detection. For DDoS mitigation, we saw back orders which utilized random forest models. We also saw encrypted traffic analysis achieving 87 to 95% accuracy without decryption of the flow, using method based on the Flores paper that we are going to briefly discuss, and a smart grid protection uh, mechanism which achieves 99% accuracy, which is 17,000, which is also 17,000 times faster than control plane based software solution. We discovered that this field particularly had 3 types of inference approaches. First is packet level inference, which inspects and classifies each packet at line rate with immediate detection without any flow aggregation. The second method is flow level inference, which provides behavioral analysis across different packets and classifying flows rather than individual packets. And finally, the combined approach, in which achieves the best of both. For example, the Joel paper, which is able to have 3.2% accuracy improvement over any individual approaches. So let me highlight some of the papers that we discussed in our survey, some of the specific systems. First is Planter. Planter identifies malicious traffic by analyzing packet level features directly in the switch pipeline. It maps decision tree based ensemble models like random forest or XGBoost. The backorders paper implements random forest models in the programmable data plane to detect DDoS attacks with very high accuracy. Joel paper uses single random forest model trained on both packet level and flow level features with unified random forest and dynamic feature weighing and achieving 3.2% accuracy improvement, with better than individual flow level or packet level inferences. And finally, Florest, which performs statistics-based classification and flow level on using flow level features like inter-arrival time for detection. So seeing all these different approaches, we also saw that the performance results from these approaches were remarkable. The response times was in few hundred nanoseconds, between 400 to 500 nanoseconds across different applications, from DDoS detection to flow level analysis. Another finding was the decision tree and random forest models perform best with the highest F1 scores due to their structured compatibility with the match action pipelines in the programmable data plane, because decision tree or tree-based systems can be fit into tabular data form, and resource efficiency of tree-based models. However, zero-day detection is still a challenge which requires unsupervised learning, which is difficult in the constrained environment and the resources on the programmable data plane. So throughout our survey, we have identified 4 key design techniques in all 3 different categories that enable applications despite the hardware constraints. First is the recirculate-and-truncate technique that enabled packet recirculation through switch pipelines multiple times for byte-by-byte packet payload processing. Second was lookup-table precomputation that converts complex calculations to simple lookup tables, as we saw in AES implementation via scrambled tables. Then is the efficient data structures like count, min, sketch, and Bloom filters that maximize the limited memory storage on the data plane. And finally, DFA or NFA implementation that maps deterministic or non-deterministic finite automata to match action tables for pattern matching. All these techniques represent the creative workarounds that make sophisticated security features possible within the constraints of P4 hardware. Despite these advances, there are significant challenges that remain. So as mentioned before, there are limited operations. That means there is no native division or floating point operations in the P4 compliant standard devices. There's memory constraint limiting to tens of megabytes shared between forwarding and security functions. There is also external dependency on requiring external CPU or external controller for complex operation that compromises the performance gains that is achieved through the programmable data plane's high throughput. And finally, again, the zero-day detection is still difficult because supervised learning-based ML models are often poor at identifying previously unseen attacks in the constraints environment. These challenges point us toward important areas for future research and development. So looking forward, we identify 4 key research directions. First is the model distillation, which is exemplified in the Trusty paper. And in their approach, they approximate neural networks with decision tree for switch deployment. Second approach is cross-device coordination, in which they use RDMA-capable NICs to access external memories like DRAM with only 1 to 2 microsecond latency impact. Next approach or next direction is complete cryptographic solution, building on Chen's AES implementation work for full protocol implementation, full security protocol implementation on the standard switches. And finally, unsupervised learning-based anomaly detection, in which initial work done by Genos represents a step towards zero-day detection within security constraints. All these directions offer promising paths for overcoming current limitations while maintaining the performance and advantages of programmable data planes. In conclusion, our survey demonstrates the fundamental paradigm shift from of network fabric, which is transforming from a passive channel to an active security layer. We are seeing orders of magnitude performance improvements over traditional server-based solutions with nanosecond response times, combined with dramatic cost reductions compared to expensive hardware-based firewalls. Novel techniques like recirculate and truncate enable deep packet inspection despite hardware constraints, opening up possibilities that seemed impossible just a few years ago. Programmable data plane represents a convergence of networking, security, and systems research that's creating new possibilities for defending against sophisticated cyber threats while maintaining the performance and demands of modern networks. Thank you so much for your attention.